Hello everyone, welcome to Mind Maps. In this video lecture, we are discussing dyes in continuation with our dyes lecture series. We have phthaleins, indigoids, and anthraquinone. Okay, so we have phthalein. We start with phthalic anhydride. Okay, this is phthalic anhydride. And then we have phenol. Okay, we condense these starting material in concentrated H2SO4. Okay, condensation is happening. Otherwise we may also use ZnCl2 H2SO4 or anhydrous oxalic acid. These can also be used. So the molar ratio is 1:2. Okay, so as you can see, we have 1 mole of phthalic anhydride and 2 moles of phenol. We get a dye known as phenolpthalien, and it is colorless. This is the benzenoid form. Okay, so let's see what we have next. Now this colorless form, okay, phenolpthalien, benzenoid form, when you add to a base, okay, the lone pair of electrons, they form a double bond, and this goes here and this goes here, okay, and this breaks. So this is how the reorganization takes place in the molecule, and we have a quinoid structure. Okay, quinoid structure, and this is pink in color. Okay, this form is pink in color. Now what we can do is alternatively, okay, the other ring can also be converted to the quinoid form, right? Is that all right? So what we have here is oxygen giving electrons, this bond breaking like this, and this bond going here, and the double bond going back to the original ring, right? It can happen like this, or either ways actually. Okay, let's just go there because that will make more sense with the diagram. So we have this structure in the bottom. Okay, so these are pink in color, both of them, and we have a sodium salt because of NaOH. So this is an indicator used in acid-base titrations. Now in very strong base, okay, when the base is very strong, what happens is we have a 3-degree carbinol and it is colorless. So this has a range. Okay, this indicator also has a range, or dye also has a range. It has a good range actually, 3 to 7. From pH 3 to 7 we can detect change. 3 to I guess 10, 9, something like that. Okay, but beyond that, when the base is very strong, as you can see, this is a structure that is formed as a result of presence of very strong base, and it is known as a 3-degree carbinol, and it is colorless, right? Now the next dye that we are discussing is indigoids. Okay, indigo is a very old dye, oldest dye, one of the oldest dyes. Okay, so this is the ancient method. So what we take here is, this is known as indican. The first starting material is indican. What it is a glycoside of indoxyl. Okay, glycoside of indoxyl, this part. Okay, so when you treat it with HCl, okay, what happens is we have a formation of indoxyl, right? You can see there is a nitrogen atom, it's a double bond O, and in air it oxidizes to indigo. Okay, this is known as indigo, and it is obtained from a plant that is known as Isatis tinctoria. Okay, however you pronounce that scientific name. Now we discuss the humans method, right? So the starting material is this, is known as synthetic indigo. We have aniline, chloroacetic acid, right? So you start with this, okay, and we have an intermediate, okay, NHCH2COH, one H from there and one Cl, okay, that is the point of attachment. CH2, HCl is removed, okay, minus HCl, okay, and when you add NaOH, okay, base is added. So what happens, this acid, okay, this acid turns into a sodium salt. We have a sodium salt. Now on further reaction with NaNH2, it is a base. At 240 degrees Celsius we observe ring closure, okay, the ring closes and we get indoxyl, right? Indoxyl from ring closure. Now when you oxidize this further, okay, we have the formation of indigo. This is deep blue in color. Okay, what exactly happens is, this is an indoxyl, okay, so 2 units of indoxyl, they fuse or undergo oxidation, okay. When they undergo oxidation, these rings fuse and we have a indigo dye, okay. This is deep blue in color, right? Deep blue. Now this indigo tin dye that we synthesized by humans method, it is insoluble in water. So what we do is, we reduce this, okay, we reduce this, and this is the reduced form. It is known as indigo tin white. It is a white powder and it is soluble in water, okay. We reduce it to form a soluble part. So what we do is, indigo tin is treated with sodium hyposulfite to make the indigo tin white, okay. It is treated with sodium hyposulfite to make the indigo tin white. Now we'll just look briefly at the dyeing process, how the dye happens. So we have an oxidized form of indigo that we synthesized. We put it in the solution of sodium hyposulfite. So what happens is, it is reduced to form indigo tin white. Now this is the fabric that we put in the vat, okay. Vat is a wooden vessel, that's why these are vat dyes. So this fabric, we put it in the wooden vessel and it undergoes air oxidation to give a blue color. It goes back to the original indigo color, right? So this is a vat dye. The next dye that we are discussing is anthraquinone dyes. So as you can see, this is a anthraquinone structure, okay. It is the X factor, okay. Like last time, this is the main structural part of anthraquinone dyes, okay. We have two phenyl rings, and they are kind of closed with a ring between, and two carbonyl groups, right, bridged by two carbonyl groups. Now how we synthesize this? This method is very similar to the synthesis of when we consider the synthesis of polynuclear hydrocarbon, naphthalene, anthracene, so the method is quite similar to that. I'd say almost similar, but let's see what we have here. We have benzene. Okay, take benzene. We need two benzene rings. Okay, so we have one benzene from original benzene, and then we have a phthalic anhydride. So what we can do is we can do Friedel-Crafts acylation. So what we'll do is we just okay, we'll just break a bond, right, and there will be an attachment set over there, as you can see. When you just flip the molecule, we have a benzene ring, the first carbonyl and the second COH that is still lying around freely. Okay, both are not attached at the same time, only one acylium ion is formed. Then we have ring closure. Okay, when you add sulfuric acid and give it a bit of heat, there is ring closure as well as sulfonation, both the things happening. Okay, so ring closes, okay, towards the lower side, and we have a sulfonic group on the second position. Okay, this is known as anthraquinone 2-sulfonic acid. Now when you add NaOH fused NaOH in presence of KClO3, you can also take NaClO3 if you have, and then we have 200 degrees Celsius temperature. Okay, very high temperature. So what happens is position 1 and position 2 we have a ONA substitution, right? ONA. Now when you add acid, what happens? We have an alcoholic groups, hydroxy groups. So this is a kind of phenol, anthraquinone 1,2-hydroxy, right? Now when you do nitration, okay, the substitution occurs as 1, 2, 3. Okay, we have nitration at third position. We get alizarin orange. Okay, these dyes are very important, alizarin compounds, alizarin orange, and when you perform sulfonation, we get alizarin red, right? Alizarin red. Now this dye is a type of modern dye, okay, and the OH group, this OH group that is formed in the dye is soluble in alkali, right? So when you have an alkaline medium, this can, you know, create problems, okay, and turn into something else. So what we use is we use these metal chelates, okay, metal compounds, Fe plus 3 Cr plus 3 Al plus 3 is moderns. So this was it for, you know, whatever we discussed. Let us just sum it up. We started with phenolpthalien, okay, phthalic anhydride phenol condensation, and then the benzenoid form, quinoid form. Okay, what happens in very strong base. Then we discussed indigoids, the ancient method, and humans method that involved aniline and chloroacetic acid followed by salt formation, ring closure, and oxidation. Then we discussed how the dyeing process takes place in indigo tin white, right? And what is a vat? Why are these known as vat dyes? Anthraquinone dyes. Okay. The synthesis via Friedel-Crafts acylation, and that is followed by substitution. Okay. So when nitration takes place, it is alizarin orange, and sulfonation alizarin red, and it is a type of modern dye. So we use metal ions. Okay, they form lakes with different metal ions. Okay, phenolic OH group, it is soluble in alkaline forms, lakes with different metal ions. So that was it for this part of the lecture. Thank you for watching.